Hey, welcome back. This is 6.4 in Calc 2. So now we're working with the logistic equation and the logistic differential equation. This is a more realistic model, more realistic than the exponential growth model because it has a limiting or a carrying capacity to it, which means that the population, unlike being an exponential growth situation, so before we had something like this when you're dealing with y equals c e to the kt. Now we're going to have kind of beginning exponential growth, but then it'll have an inflection point and then level off at some number which we'll designate as L. Okay, so it'll sort of level off there. And it's more realistic because in the real world, populations of animals will eat all the resources, and so just geographically they'll exhaust the area they live on. If you have billions of people living on an island, it's not going to work out very well. So people start falling off the island and dying and that sort of thing. So more realistic, and so yeah. So let's define this thing. Definition. So the differential equation for exponential growth was that the population, the rate of change of the population was proportional to the population. Our new definition for the logistic growth formula will be that the rate of change of the population is proportional to the population, but then times this factor, and this factor works as kind of like the limiting factor. So once y goes above, or once y goes above, some number L, the population, the rate of change of population will be negative, it'll be going down. Up until that point L, though, it'll be growing. Okay, so in the end, if we solve that differential equation, which I'm going to show you how to here in a sec, you'll end up with y equaling a more complicated formula, L all over 1 plus b e to the negative kt. All right. So L is going to be our carrying capacity. And the k value will be greater than 0, and L is also greater than 0. Okay, so this is our information for today, and the other guy was what we saw in the previous section. Okay, so let's look at solving this thing. It's example 1 in the book. And it requires what's called a partial fraction decomposition that we'll study in 8.5. Sometimes a pre-calculus class will teach you that, but I'm not sure if everybody's seen it. So anyways, what do we have? The differential equation. Right, so we want to separate first off. So starting with this guy right here, this is our logistic differential equation. We're going to separate in our first step. Okay, so that equals ky times y minus y over L, 1 minus y over L. Okay, so I'm going to move the y times 1 minus y over L to the left side. So I have y times 1 minus y over L. On the other side, I just have the constant k dt. I'm going to rewrite this left side in the denominator by factoring out a 1 over L from the 1 minus 1 over L, y over L term. So I get 1 over L times y times L minus y. Okay? And that'll equal k dt. And you can see if you redistributed the 1 over L into this, you end up back where you started. Okay, so hopefully that's not too big of a leap of faith. Once you have the 1 over L in the denominator, you can flip it and put it into the numerator. So technically it's 1 over L, but that's the same as L. So you can rewrite this expression as L dy all over y times L minus y, and then that will equal k dt. Okay, then you want to integrate both sides, and here's where they do the magic of the partial fraction decomposition in the book. The long story short, you don't have to know how to do this right now, but it's just a way of breaking a fraction into two fractions over the factors in the denominator. Okay. So you see that how they have, there's two factors here in the denominator. Later we'll learn an algebraic process to, it's kind of, basically you're undoing the process of finding a common denominator and adding over the common denominator. All right, so we'll learn how to do that later. And it's not just a matter of, putting 1 in the numerator. We got lucky this time. So anyways, long story short, there that is. Over here, k dt. Now I'm going to go ahead and integrate both sides. So I get the ln absolute value of y plus ln absolute value of L minus y times -1, though, because there would be, you'd probably have to do a u sub, right? So u sub on L minus y, and then your du would be negative dy. So that would give me du equaling negative dy. So you would end up with a negative in front at the end of the day. And on the right side, you would have kt plus c. Okay. Then I'm going to combine these two natural logs using a quotient rule of natural logs and rewrite that as y all over L minus y. And then this equals kt plus c. Then I'm going to exponentiate both sides. And I'll have a y all over L minus y, so when I exponentiate, equals e to the kt times e to the c. Then I'm going to drop the absolute value, flip-flop the order, and have a plus or minus, but replace plus or minus e to the c with just a big C, and then e to the kt. I did it a little different than the book. They have a negative, so that there's a little bit less work to worry about. Anyways, I'm going to now multiply both sides by L minus y. I get y equals L minus y times c e to the kt. Then I'll distribute, so y equals LC e to the kt. Minus y c e to the kt. I'm going to move all the y stuff on one side, so y plus y c e to the kt equals L c e to the kt. Factor out the y on the left here, so you get 1 plus c e to the kt. Over here, L c e to the kt. Divide both sides by the 1 plus c e to the kt. You get L c e to the kt. All over 1 plus c e to the kt. Divide top and bottom by c e to the kt. And we're getting then y equals, so I'm multiplying both top and bottom by 1 all over c e to the kt. It'd probably be better just to multiply by, no, sure, yeah, 1 all over c e to the kt, that's fine. We'll just have to do some fancy footwork here in a sec. In the numerator, you just end up with L, the limiting capacity. And the denominator, if you distribute, you get 1 all over c e to the kt plus 1. I'm going to rewrite that denominator now. So first I'm going to use the commutative law of addition and put the 1 first. Then I have 1 all over c times 1 all over e to the kt. I'm going to replace that constant 1 over c with just a variable b. So I get L all over 1 plus b, and then you could write 1 over e to the kt as e to the negative kt. Okay, so lo and behold, that's our general solution for this differential equation. And the more realistic part of it now is that as you go towards infinity, the population isn't going to grow exponentially. So if you take a look at the limit as t goes to infinity, of L all over 1 plus B e to the negative kt. The limit of this thing is the limit of all the individual pieces, right? So the limit of the constant is just a constant. So the limit of L up top is just L. The limit of 1 is just 1. And then you're worried about the limit of B e to the negative kt. You could rewrite that as the limit of B all over e to the positive kt. And then as t goes to infinity, this thing is, the denominator is going to go to infinity. The numerator is just some constant, we'll call it c. So when you have that form, it's going to go to 0. So you'll have 1 plus 0 in the denominator. In other words, L over 1, which is L. And that's the limiting capacity that you see in the picture in figure 6.19 and kind of what I was talking about up here as well. So this number L, the limiting capacity, that's what it approaches as time goes to infinity. So it becomes more realistic and yeah, it's better for modeling population growth. Okay. So there's our formulas. Let's show that these things actually work in the differential equation. So here I have y equals 4 all over 1 plus 2e to the negative 3t. The differential equation then that's associated with that is, of course, k times y times 1 minus L over y, or y over L, rather. You could see k and L from the original equation. The k is just whatever's in front of t, so in this case it's 3. Don't use the negative, it's not negative 3, it's just 3. The k value is always positive. Then the limiting capacity is just whatever in the numerator, so 4. So our differential equation that we're trying to kind of satisfy is going to be 3y times 1 minus y all over 4. Okay. So what I want to do is basically find the derivative of this logistic equation and show that it's equal to the right-hand side of the differential equation right here. Okay. So this is my goal. And I wouldn't ask you to do this on a test. It's just, and I don't even think the homework asks you to do it. It's kind of a good exercise in derivatives. And okay, so let's try it. So I have, let me rewrite y first off. So I note, just for the sake of easier differentiability, y is equal to 4 times 1 plus 2e to the negative 3t to the negative 1. Okay. So I take the derivative of that y prime, and remember the goal in mind. I have that red thing in mind. I want that at the end. So anyways, taking the derivative, I use first the power rule. So bring down the negative 1. So negative 4 times 1 plus 2e to the negative 3t. Negative 1 minus 1 is negative 2. And then the chain rule, I have to multiply by the derivative of the 1 plus 2e to the negative 3t. So that's going to be 2e to the negative 3t times negative 3 with a chain rule on that, right? So it's going to end up being ultimately negative 6e to the negative 3t. Okay, now I'm going to go ahead and rewrite it a little bit. I'm keeping that goal in mind. So I'm going to rewrite it. The negatives will cancel each other, and I could write 4 all over 1 factor of this, okay? So it would be 1 plus 2e to the negative 3t to the first power. And I did that because that thing right there is y. And if you look up here, that's kind of, I want a y in my first position with a 3 in front of it, but we'll get there. So anyways, then it'll be times, yeah, let's go ahead and put that 3 out in front. So if you factor 6, what is 6? It's really 3 times 2. So I can take one factor of 3 and plop it here. So I have 3 times y. And then take the factor of 2 left over, and I have 2e to the negative 3t. And then the other factor of the 1 plus 2e to the negative 3t, and plug that downstairs here. So it's 2e to the negative 3t. Okay. Okay. Here you can see we're starting to get it. I need to get this 1 minus y over 4. And you could do long division on this thing, but there's another trick you can pull, and that's just by adding and subtracting 1. So if I add 1, look, I have the exact same thing as what I got in the denominator. And then I just subtract 1 on top of that to keep everything good. So I end up with 3 times 4 all over 1 plus 2e to the negative 3t. I'm going to sort of chop this new fraction into 2 parts. It'll be this fraction minus this thing. Okay, so I'll end up with times 2e to the negative 3t plus 1 all over 2e to the negative 3t plus 1, that's just 1. And then minus 1 all over 1 plus 2e to the negative 3t. Okay. And now look at how close I am to my goal. It's almost there, right? All I need is that y over 4. Right now I just have 1. So you could cheat a little bit by multiplying by 4 over 4 on that second term inside the parentheses. 2e to the negative 3t. So I get 1 minus 4, and then put a 4 kind of in the denominator as well, right? So 4 over 4 is just 1, so it's no big deal. 2e to the negative 3t. And then you see I kind of got it, right? Because this part right here is just y. And then the 1 over 4, kind of, you could cheat and put a 1 there. That's the limiting capacity. That's the L part. Okay, so you pretty much nailed it from that point. So you got 3 times y times 1 minus 1/4 times y again. So I know it's a bit weird. You're probably not used to seeing that kind of back engineering. But at the end of the day, then that's your 3 y times 1 minus y all over 4, which is the right side of that differential equation, which is what we were trying to show. Okay, so this logistic equation satisfies the logistic differential equation. Okay, great. What's the upper limit of this differential equation? Well, it's just 4. All you have to do is look at the numerator. They do a nice little picture there. And again, they talk about taking the limit of this thing as t goes to infinity. So you would have 4 all over 1 plus 2e to negative 3t. The limit of 4 would just be 4. The limit of 1 would just be 1. And then the limit of this thing, from what I already showed you before, you could rewrite it as 2 all over e to the positive 3t. And then if you're plugging in values of t that are just getting bigger and bigger and bigger, like 10, 100, 1,000, this is going to be some number c all over infinity, which will eventually be 0. You know, get really close to the number equal it, but it will get close, right? So you get 1 plus 0 in the denominator. And so as time goes to infinity, it's going to 4. Okay, so anyways, getting back to this idea of the difference between the exponential growth equation and the logistic differential equation over here, you see it kind of starts out like an exponential growth, the logistic guy does. So in red here, it's kind of like an exponential, but then it bends over and the concavity changes. Okay, from Calc 1, you know that when concavity changes, you have an inflection point. And what we want to know is, where is that inflection point? Because that will represent where the rate of change of the population is the greatest. And I always talk about like zombies. When is it super serious that you don't want to go outside? I don't want to say it's safe, but it's safer to go outside when there's only 1 zombie as opposed to when there's 1,000 zombies. Okay, so the rate of change of you potentially becoming a zombie is going to be the greatest at this inflection point. Once you get beyond that, pretty much everybody is a zombie. So you can almost expect to become a zombie after that, and you might as well just go outside anyways. I don't know. I would stay inside with my, my zombie defense kit. Yeah. So anyways, determining that inflection point, that's what they're doing in example 4 here. Let's take a look-see. So we have y equals 4 all over 1 plus 2 to the negative 3t. Okay, so L in this case is equal to 4, K is equal to 3. And to get the inflection point, what we're going to do is basically take the derivative of the derivative. Okay, so if you remember finding inflection points, it was find the second derivative, set it equal to 0, solve it, and those would give you the potential inflection points, right? So that's kind of what we want to do here, sort of. But I know it's going to be a nightmare, because if you just look at the first derivative, just getting that thing is kind of nasty. And then so here's the first derivative. If you take the second derivative of that, you're going to have to do a product rule, and then you're going to have to, it's going to not be a good day. Okay, so what we're going to do instead is work with the differential equation and take the derivative of that implicitly. So we can write our differential equation because we know the L and the K, we could write it, right? So it's 3y times 1 minus y all over 4. Let's go ahead and distribute. I don't think they do that in the book, and I think it's a little easier if you just distribute. So 3y minus 3y squared all over 4. And then we differentiate that implicitly. So the second derivative with respect to t is going to be, okay, the derivative of 3y is 3 times 1 times y prime. And then minus the derivative of this thing will be, bring down the 2, so you'd have 6y all over 4, which would be 3y all over 2 times y prime. Okay, you could factor out the y prime, and then you just have 3 minus 3 halves y. Okay, then you're going to take this part and set it equal to 0. Okay, where the derivative equals 0, we kind of already know. The derivative will equal 0 exactly where this thing is equal to 0, and that's going to be when y is equal to 0. That's when the population is 0. It'll also be when 1 minus y over 4 equals 0. And where is that? Well, that's the limiting capacity. That's when y is equal to 4. So we need not really bother with these two numbers, because those are the places where the graph is of the same concavity. It's not changing concavity. So we need not worry about the y prime part. We just take the 3 minus 3 halves y and set it equal to 0. Okay, and then solve that. Right, so I'll have 3 halves y equals 3, multiply both sides by 2/3, so y will equal 2. Let's make sure that's what they got. Yeah, and then we need to find the other coordinate for this, so the t value that goes along with this. And in order to get that, because they want to know not only what is the inflection y value, but you want to know where it happens or when it happens, right? When is it a bad idea to go outside when there's a bunch of zombies, right? When is it most likely that you're going to get bit and turn into a zombie when you're not a zombie already? So I'm going to go back to the original logistic equation and plug it in there and solve for t. So I have 2 equals 4 all over 1 plus 2 to the negative 3t. You can cross multiply, get 1 plus 2 to negative 3t equals 2. 2 to negative 3t equals 1. You could take the natural log on both sides if you wish. So ln 2, ln 1. So you'll have negative 3t, and something's wrong, isn't it? Divided by 2, negative, 1 plus 2 to negative 3t, negative 3t, negative 3t ln 2 equals, well, ln of 1 is 0, so that's kind of an issue. Hold on, I did something silly. Oh, I see it. There's a mistake in the book. I didn't even, oh my gosh. The equation is written incorrectly. It should be 2e to the negative 3t, like that. Sorry. I don't know what the heck I was thinking. 2e to the negative 3t, 2e to the negative 3t, 2e to the negative 3t. Okay, so here then, let's just start this over. I'm going to cross multiply. I get 1 plus 2e to negative 3t on this side, and then 4 divided by 2 is just 2 on this side. I get 2e to negative 3t. Subtract the 1 over, I get 1. E to the negative 3t equals 1/2. Natural log on both sides. And I get negative 3t equals ln of 1/2. And then t equals negative ln of 1/2 all over 3. So the inflection point is going to be negative ln of 1/2 all over 3, comma 2. Okay. The y value is always going to be L all over 2, as it turns out. So this is always the limiting capacity divided by 2. And you would see that if you just did this process in general. So if you just left the L in there instead of putting in a 4 and left the K there, you would see that it just turns into your y equaling L over 2. Okay, so that's kind of, you can assume that from this point on. Anyways, there's that. So, yeah, they mention it here. The point of inflection occurs at y equals L over 2. This is true for any logistic growth curve that starts below the carrying capacity. So this, of course, is all in with regards to being below the carrying capacity. If you're above the carrying capacity, the curve will kind of look like this. Okay, so the population will die down to the carrying capacity. Animals or people will die until. Okay. Graphing slope fields and solution curves, great. I think maybe we should look at the homework. Yeah, let's do this. Let's see, it's an Elkhorn. Yeah, sure. Let's do this guy. Maybe we should just go to Webassign and do one that's similar in there. So yeah, let's go to Webassign and try one of these. The only problem with this is I don't have the answers, so just bear with me if I get the answer wrong. Let's find the initial condition. You just plug 0 into the logistic equation. It's 12 for this guy. T, if you let, no, it's 12/5. So you just plug t equals 0 in there. So the other ones you can graph using my math lab or Desmos. Let's try this character here, this number 4, and I'm pretty sure this is like the example in the book. Okay. So number 4, logistic equation is given as 3400 all over 1 plus 33e to the negative 0.4t. So the L value is 3400, the K value is 0.4. And those are the first two questions. You know, make sure you're not plugging in negative 0.4. It's positive 0.4. The L value 3400. Use the equation to find the initial population. So plug in 0 for t, the initial population at time 0. So you get 3400 all over 1 plus 33, which is 3400 divided by 34, which I guess is 100. Okay, so 100 people in the beginning, 100 things. Use the equation to determine when the population will be 50% of its carrying capacity. So this is basically a pre-calc problem. Just go 1/2 times the carrying capacity equals 3400 all over 1 plus 33e to the negative 0.4t. And you're solving for t. So I'll sort of cross multiply. This will be 3400 all over 1/2 times 3400, which will just be 2. Move the 1 over, so you get 33e to negative 0.4t equals 2 minus 1 is 1. Divide by 33. Is 1 over 33. ln on both sides. Okay. So you get negatives. Let's make this the video quiz as well. So this is the video quiz, 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 video quiz. I'll mark down in the notes. This is problem. This is a 6.4 video quiz question, and it's problem 4 from Webassign. So POT is 3400 over 1 plus 33e to the negative 0.4t. Okay. Let's see what we get. Negative 0.4t equals ln of 1 over 33. Then multiply both sides, or divide both sides by negative 0.4. And you get negative ln of 1 over 33 divided by 0.4. Okay. So they want 4 decimals on that thing. Let's go to, I like to go to Wolfram Alpha, but they stopped giving me decimal approximations, so I can't use it anymore. They are cheap. They're trying to get you to pay for the subscription. It's not going to happen for me. Sorry. Keeping my money. 0.4 and 8.7 seconds. So 8.741 3, depending on how many decimals they want. 4 decimals. So 8.741 use the equation to write the logistic differential equation. Well, that's easy because we have all the information we need for that. So it's just dy over, or dp. So be careful. They're going to want everything in terms of p. So dp all over dt equals 0.4y times 1 minus y all over 3400. Okay. So that's sort of label your answers for me. Here's part B, here's part A. This is part C, I believe. This was part D. And this is part E. Okay, so let's put that in there. And then we'll make sure it's right. So I don't know if it's right or not yet. Minus y all over 3400. Oh, and it has to be P. See, now that would have been a nightmare if you not realize it needs to be in terms of P. And it needs to be capital P as well. We nailed it. All right, so there's that initial condition. And the logistic equation to solve for that. I'm curious as to see how this number 5 kind of works. I've not seen this problem before. What do we have? It seems like you just read the k equals 1 and then the L equals 27 right off that, and then your logistic equation should be 27 all over 1 plus, oh, you don't know the b value, be to the negative kt. So to the negative t, and then you're using the initial value to solve for the b value. Okay, so that'd be 3 equals 27 all over 1 plus b e to the 0. E to the 0 is 1. So you get 1 plus b equals 27 divided by 3 is 9. So b is 8. So we get that thing, and then we use it to. So you get 27 all over 1 plus 8e to the negative t. And then you just use that equation for like y of 5 and plug 5 into that equation, plug 100 into that equation. And yeah, okay, so no big deal there. This one looks annoying, so let me show you how to do my example. So number 7, the Panther problem. So originally you have 35 Panthers, so that's an initial condition, 0, 35. After 4 years, there's 134 Panthers, so 4, 134. The carrying capacity is 350 Panthers. Write a logistic equation that models, and they want you to round k to 4 decimals. Okay, so our logistic equation, as it sits, is y equals L, which is 350, all over 1 plus b e to the negative kt. So here you use the initial conditions to solve for b and k. So first plug in 0, 35. E to the 0 is just 1, so you got 1 plus b. 1 plus b then will equal 10, so b is 9. And so our equation becomes y equals 350 all over 1 plus 9e to the negative kt. Use the other initial condition now to solve for k. Negative 4t. And then solve for t. A little bit of arithmetic. Take ln's. Divide by negative 4, and that will give us, that should have been k. Sorry, we're not solving for t, that's k. So this was k throughout. Sorry about that. And that'll be negative ln of 24 all over 134 all over 4. And then get your 4 decimal approximation. So ln 4 divided by 134 is 0.4299. 299. Is it 4 decimals? Yeah. Okay. Then we can rewrite our equation using that intel. So we get y equals 350 all over 1 plus 9e to the negative 0.4299t. And I suppose we'll be using that then. I'll put it in here. So 350 divided by 1 plus 9e to the negative 0.4299t. Find the Panther population after 5 years, so you just plug 5 into that formula. So y of 5, and I'll plug it and chug it in my calculator. Divided by 1 plus 9 to the negative 0.4299. 4299 times what, 5? The denominator, so 170 Panthers. 170. Now to nearest whole number, 171. When will the population reach 175? And note that value there, so this is part B, this is part A. The value that they're looking for there is the inflection point. Okay, so 175 is just half of L. Anyways, you're literally going to have to plug it in here, and then solve for t regardless. So 1 plus 9e to negative 0.4299 t. So it's going to be 2 1 9th ln divide and 2 decimal approximation, second ln 1 over 9 divide 0.4299, I'm getting 5.11. 5.11 years, which makes sense because that's a little longer than 5 years, and after 5 years you have 171 Panthers, right? So it seems like we're on target. Part D, they want the logistic differential equation, so dp over dt equals k, which is 0.4299, times y, which is p, actually for us, times 1 minus y all over the 350, or p all over the 350, sorry. This will be a p. So we get 0.4299 p times 1 minus p all over 350. Oops. And then we want to use Euler's method to get, all right, so to get Euler's method to work, I'm just going to go to my computer, my Euler method calculator, and I usually use the Planet Calc version. So y prime is this 0.4299p. Maybe we need to put in some multiplication symbols so the computer doesn't have a fit on us. And they want to use y, so we'll use y here. 1 minus y all over 350. The initial x, for our case t is 0. The initial y is 35 for 35 Panthers. Point of approximation, we want 5 years. And the step size will go by ones. They tell you h is 1 in the question. And we want the nearest whole number in our approximation, and it's being a jerk. I killed it. Maybe you literally have to write the y prime equals. I wasn't very happy about that. Let me try this first, so it's kind of already in there. Go backwards. And then exact solution. Approximation 5. 35. 0. And then let's put it in now. Let's see what flips on us. 299 star y star 1 minus y over 350. And parentheses, and calculate. Yay. So let's say I got 152.03. We'll go with 152. Notice the actual answer, 171 from our logistic equation. So this is just an approximation. And they want to know, when is the panther population growing most rapidly? That's just the answer from part C. That's at the inflection point. And submit and see if it's right. Drum roll. Yay, we nailed it. Okay, so I think that'll do it for us in this section. As usual, thank you for watching, and I'll see you next time.